Now that I think most of us are here, I would like to introduce our keynote speaker, Samuel Gross. Samuel is a security researcher at Google Project Zero. He works on browser security, finding bugs that could put millions of users at risk. Before that, he led the development of the V8 Sandbox. This is a super important mitigation in the V8 JavaScript engine that prevents bugs from turning into critical security vulnerabilities. Samuel, take it away.
Yeah, thank you. Is the microphone working? Cool, perfect. Got some technical issues. Let's hope they resolve. But yeah, thank you for the introduction. My pleasure to be here. Thanks for bringing me here. So yeah, my name is Samuel. I work at Google. As you just said, Marco, I worked in the V8 team until kind of mid last year. And then I moved back to Project Zero, which is the security research team in Google. But kind of the common theme is that a lot of my time I spent on trying to make JavaScript engines more secure. And so this is kind of what I'm here for today, specifically to talk a bit about the V8 Sandbox, which is like a sandboxing, in-process sandboxing mechanism we're building for V8. Yeah, I guess the story I kind of want to tell is how V8's approach to security moved from basically kind of just trying to write correct code to still trying to write correct code, but also building these special mechanisms for kind of containing vulnerabilities at runtime. Yeah. I want to start with a bit of motivation, kind of why are JavaScript engines a relevant topic, security of JavaScript engines, why is that relevant? So here I have a bunch of headlines from, kind of go back 10 years, the oldest one you see is on the left in the middle from 2016. And these are all kind of, the same kind of headline, right? Some browser got exploited, there was an attack in the wild, and all of these were vulnerabilities in the JavaScript engines. So yeah, it's really kind of a focus for attackers to look at these engines and find vulnerabilities there and use them for these kinds of targeted or semi-targeted attacks. So yeah, here we are looking at kind of 10 years of JavaScript engine attacks. Yeah, so I think that raises a few questions. Maybe one question would be why, what's so special about JavaScript engines? Why are there maybe so many bugs, or why do they get attacked so frequently? So for that, to explain that, I want to start with something that's not JavaScript. So here, this is some C++ or C program that I made up. You see this function get, which returns a value in an array. It gets an integer index passed in, and then it returns that element. It does attempt to do some sort of bounce checking, right? So you see there's an if condition. However, this isn't quite working because the index is assigned integer, right? And so if you give it a negative number, this bounce check thing would succeed. It would say, yes, this is fine, but then it actually does go out of bounds right afterwards. And so if an attacker was able to reach this function with their own controlled index, this is how they could cause memory corruption. Now, this type of bug is well known, right? We know this sort of problem for 40 years or so, and we kind of understand this is a solved problem in some sense. The compiler can fix this for you, right? So if you think of memory safe languages like Rust or Go or Swift or Java or whatever, they don't have these problems. And the reason for that basically is that in these languages, the compiler also inserts a bounce check before every memory access, right? And so in the compiler, kind of what it would do as in one of the earlier phases, it would add these its own bounce check operations before every access. And then if they fail, they might terminate the program, a Rust panic or something. But it terminates in a controlled way. It's not memory corruption. Now, what happens if our program is actually correct, right? So in this case, all I did was change this signed integer to an unsigned size t. And now this works correctly. Now this bounce check is actually correct. So what happens now? Well, first, the compiler still does the same thing. It still adds its own bounce check to protect this memory access. However, later on in its optimization phase, the compiler would realize, oh, there's actually no way I could get to this bounce check with I not being in this range, right? And so it can prove that this check is redundant and it eliminates it. And this is actually quite important for performance because it means like a lot of these bounds, like a lot of the memory safety kind of comes for free if the compiler is able to prove that the access is indeed always safe. Right, and so with that, let's take a look at some JavaScript example. I promise this is the only JavaScript you have to read today. This is like somewhat similar, right? So we have also an array object and a get function that takes an index, but now it also takes some like multiplier, some m value, and it multiplies the array element with that multiplier. Yeah. Again, here we have a bounce check, so actually we also like one that should be correct, right? So we check if it's less than 0 or if it's larger or equal to the length, and then we do this access. So let's take a look at how a JavaScript compiler would deal with this. So one of the first things it does is, and this is true for pretty much all compilers, it would convert it to its own kind of intermediate language that it knows how to optimize on, right? Most of this is not like particularly JavaScript specific, except for the speculate instruction at the start, because as you will see as you can see in the JavaScript code, there's no type information for the compiler, right? It just gets I and M. It doesn't know if it's integers or whatever, and so the compiler kind of based on previous executions, it has to speculate about types, and then it has to guard against the speculation becoming invalid in the future. And so for this case, it might have seen that in the past, I was always like an integer, like a SMI. SMI is like small integer. So it would speculate that I will continue to be a SMI in the future, and it adds the speculate operation, which is nothing more than kind of a, is this an integer? If not, like bail out, go to the interpreter or something. But from that point on, it's kind of, it looks like kind of regular intermediate language code maybe. So we have the bounce check, right? We have the two-number conversion. And then like there we also have this bounce check added by the compiler, right? Before the array access. Because JavaScript is supposed to be memory safe. So yeah, you need some sort of checking there. Now, like, okay, now we do actually kind of the same thing that our previous C compiler or C++ compiler did. Which is that we realize, okay, actually there is a check for I, and it cannot be that I is, not in this range at this point in time. And so, okay, we again eliminate this bounce check. The problem is there's something in between. There's a two-number conversion in between, and that is something that is not side effect free, right? So in this case, here's an example where an attacker could abuse this to cause memory corruption, because in JavaScript, the two-number conversion, that's a very complex operation that can potentially trigger arbitrary code to run. So in particular, if you give it, if M is an object that has a custom value of method, which is used for converting to primitives, then this method will be invoked during two-number, and it can resize the array, right? And in this case, it might resize it to 0. And now we have a problem because we eliminated this bounce check thinking that I is always in bounds, but actually we did the bounce check against the length 100, but then at the time of the access, the length is 0, right? So this doesn't work. And so we have kind of done the same thing, but now it's insecure, and it's actually the cause of memory corruption and not the fix. So, so yeah, I think maybe another way to try and explain why JavaScript engines are a bit special is by thinking of kind of the technology stack that makes up a typical application. So if you think of something like an image parser maybe, that is also exposed to untrusted data. The technology stack might look like simplified, but it might look something like this, where the bottom you have the hardware, then you have the compiler and runtime that compiles the code of the image parser, and then the data is consumed and is processed by this code. And in terms of the attacker model, you have the attacker controls only the data, so only the image that goes in, and the code is like written by a trusted developer, but it may have bugs, right? And so that is the attack surface. But the compiler and runtime are kind of one step removed, and so they can guarantee memory safety at this level. So why do I say one step removed? So if you compare this to a JavaScript engine, the picture looks a bit different, because there the code for the compiler, so JavaScript or WebAssembly, they are directly attacker controlled, and they also operate on attacker controlled data, like runtime objects and that sort of stuff. And so in this model, the compiler and the runtime are directly the attack surface. And this makes it really hard to guarantee memory safety at that level, because any bug there is potentially a memory corruption problem like we just saw. Right, I mean, maybe another way to think of this is that, you could imagine, or I think it's quite likely, that compilers like Rust or Go or so, these compilers probably have bugs, and these bugs would lead to insecure machine code being generated, but they don't really matter, because to trigger these bugs, you have to give the compiler like malicious Rust or Go code, and then execute the result, at which this is just not an attacker model, right? Like if the attacker can run arbitrary Rust or Go code, like what do you want? And so this is kind of a fundamental difference in the JavaScript world. To make this point a bit more clear, this is a slide I made 3 years ago. I'm not gonna walk through all of this now, but there's a talk you can watch. What I'm trying to do here is, oh no, hope it comes back. What I'm trying to do here, yeah, perfect, is kind of show how different optimizations in the compiler, come on, come back. Sorry. Okay, let's hope it sticks. How different optimizations lead to different types of memory unsafety issues, right? So the red circles, they are the types of memory unsafety issues we kind of commonly have, like type safety and maybe spatial memory safety. And then there's like lots of these optimizations that a compiler would do, like common sub-expression elimination or loop invariant code motion, these sorts of things. And then like there's different bugs that are like these CVE numbers that happened in these phases, and then you can kind of trace these nodes and edges. They form kind of a path of how did this specific bug end up leading to memory unsafety, right? And so you can, for example, see there's this one here, like there's bounce check elimination. There was a bug in the bounce check elimination logic. While you can easily imagine how that leads to memory unsafety, right? Like if the bounce check is wrong, it straight up goes out of bounds. Less obvious are kind of these ones down here or here maybe, where like kind of a subtle logic issue in some analysis further away leads to confusion of other optimizations, which then like maybe confuse like yet another thing, and then ultimately they also end up causing maybe an incorrect bounce check, or like the length of an array to be incorrectly set or something like this. Yeah, I guess what I want to say here is that it's not the case that you have this one type of bug in the compiler that always happens. It's always like just this one type of issue. It's really kind of the whole picture of there's a good chance that a logic bug in any of these optimizations, there is some way where that can lead to memory unsafety later on in the compiler. And so yeah, this is where this is from. Okay, so we've kind of answered now. So why are JavaScript engines relevant? Why are they kind of special? Maybe what's still a bit unclear is why are there so many problems? Why are there so many bugs in these engines? And I think that is also relatively simple, maybe. I like the way I would explain it. It starts with the requirements. So we want our browser to go fast. We want these engines to go fast. We want the code to run fast. So we have these performance requirements. And this is kind of in combination with a very complex and evolving spec. So JavaScript is really kind of a terrible language to make go fast, but then we want to make it go really fast. And so this creates a lot of friction. And so this pretty much directly leads to a very complex code base, right? So if you want JavaScript code to run really fast, well, you've got to do all of these optimizations, you've got to do these speculations on types, all of this stuff. So you end up with a quite complex code base, which means that if you work a lot on this complex code base, you know, the language is evolving, you're implementing new features, you are implementing new optimization, you're going to make mistakes and bugs are going to happen. And kind of as we just saw, like every logical error in a compiler or runtime, there's a very good chance that it actually also is a security bug, because there's some path where it ends up leading to something unexpected. So this was kind of the motivation and background, maybe. What can we do, right? So how can we make this a bit more secure? And I think for that we can kind of look at the same picture and try to see, like, you know, is there any one of these steps that we could break? We could start here, right? And we could rethink, you know, do we actually need to make these things go fast? It's maybe not the most relevant question for this audience, but let's dive into it a bit. Like one option here is disabling optimizing compilers, right? So in these JavaScript engines, you have typically a lot of compilers. You maybe, like in V8, JavaScript gets compiled through 4 layers of, like, there's 4 different compilers or execution tiers. And the question is, could we just disable kind of the heavyweight ones to reduce some attack surface here, right? So this, this works to some degree, right? So you can get maybe like a 50% reduction. We have this spreadsheet which is public on kind of bugs that we know are exploitable, and there we have a few properties that we track. For example, would disabling a compiler have mitigated this bug, right? And you see, like, this is this column here. There's green and red in here, so it's kind of 50-50. Maybe like half of the bugs are in these optimizing compilers and the other half are elsewhere. But of course, this can come at a dramatic performance cost, right? So it can be anywhere from 5 to 90%. Like, really depends on the workload. If you have a static web page, well, I mean, you're not really going to notice. If you have some, I don't know, maybe like Photoshop in the web or so, this exists. It needs heavy optimizations to work smoothly or at all. Like there you will definitely notice. I guess what I would say is, okay, like maybe it's 50% bug reduction, so this is good. This is a useful tool. One thing to keep in mind is kind of bug count is a metric, and I guess what you actually more care about is like something like, you know, users getting harmed or attacked by exploits. And these are not the same thing, right? So if you reduce the number of bugs by 50%, that doesn't mean that there will be half as many attacks, because that would assume that every kind of attacker just has one bug, right? And that's very unlikely to be the case. They typically have more than one bug in their repertoire. So I would say this isn't the solution, but it can be a useful thing to do. Okay, let's look at the next kind of chain here. Once the projector comes back. Should I? The live stream still works, so I think. Okay. Okay, so it's just the projector maybe rebooting or something. Anyway, I don't, like, the next slide is not super full of anything. I can just go on. So the question was basically, you know, can we kind of prevent that these performance requirements lead to a highly complex code base? Yeah, it would be. It's really turned off. That's Is it restarting, or what is it doing? Sorry. Okay, it's back. Thank you. Perfect.
Just in time.
Exactly. Exactly. This is actually all just planned. I'm just like rewriting the slides now. This is but okay, no. So yeah, I guess again, like the kind of this is here. Here's where we are, right? So can we prevent this from happening? Oh no! What? Oh.
On a un petit souci projecteur, je pense. C'est la première fois, mais il y a plein.
Gonna have like a 5 minutes break, so they have time to restart it. And there's some problem with the frequency of the projector, it seems. So like 5 minutes break, and hopefully we restart. And sorry about that. Okay, cool. It looks like we're back live. Fingers crossed. Go ahead.
Okay, perfect. Okay, thank you so much. Right, let's do a very brief recap, right? So this is where we are. We kind of investigating what can we do based on kind of this flow diagram. Yeah, can we somehow avoid like the requirements leading to a complex code base, basically? Like it seems difficult, right? Like I think like just based on the fact that you're trying to make JavaScript, which is like has this hugely complex spec, and you're trying to make that go fast, I think there's like a baseline level of complexity that you will struggle to get below, basically, and that baseline level is still way too high. I mean, I think there are examples. This is a blog post from last year where V8 is trying like fairly big changes based on the thinking that this should reduce complexity to some degree, right? So this is a major refactoring where the optimizing compilers in V8, they are moving away from a sea of nodes representation, which is kind of, you know, all of these operations, they just kind of flow. You have a big soup of compiler compiler operations, and then you like use that as your intermediate representation, and then they go now moving to kind of classic control flow graph based IR, because basically what it says here, like the sea of nodes turned out to be too complex. It adds even more complexity. So there is some examples for this, but I think there is a baseline level of complexity, and that is still too high. Right, so next step would be somehow avoid code complexity leading to bugs, right? So this is, I think, what most people would intuitively go for. I mean, yeah, in theory, we know how to write correct compilers, right? In practice, bugs happen, right? Like testing and fuzzing are definitely crucial. Like one of the main fuzzers that V8 is using is this Fusilli, which is also open source. Like they do work, they do find a lot of bugs, but there is also kind of a ceiling to what they can achieve, right? Like at some point we looked a bit into kind of what is the rough level of complexity that these fuzzers can trigger, like can find, and there's definitely a lot of bugs that are just basically too complex. Like you need, I don't know, 15 different pieces to come together to trigger the bug. And for the fuzzer, it's just too far away. It'll like the kind of the search space of all possible JavaScript programs is just so astronomical big that a fuzzer is just not going to cover a relevant part of it ever. I guess what I would say is that like this is a big hard problem, right? Like writing bug-free code in a complex code base, that's a big complicated problem, and the security strategy should not be, yeah, we just write bug-free code, fingers crossed. That's not gonna lead to a great outcome. So kind of like I guess one other option that maybe goes into this this space here is can we do verification, some sort of formal verification or whatever, and basically look at maybe what the compiler produces and try to prove that this code is correct, right? I have an example here for how that might look in practice and why it is hard. So this would roughly correspond to quite heavily optimized version of this JavaScript code, which just kind of sets a property of an object to the result of some function call. So the register RAX is object A. The way so if a like proper JavaScript optimizing compiler optimizes this code, roughly what it ends up doing is first it needs to check what A is. So this is kind of the same thing I described before, where the compiler would look like how did this function get called in the past, and it would see, okay, maybe A was always a certain object of a certain type. And in V8 these types are called map object. Like a map is kind of a type description object for JavaScript objects. And so the compiler would insert a type check that would look like this, where it looks at like, is the kind of first pointer in this object, is it this pointer? And then I know the type. Don't get confused about the -1. The -1 is because V8 uses tag pointers. So every pointer has a 1-bit set, which indicates that it's a pointer and not an integer, which means if you dereferences, you always have to subtract 1, right? But it's basically just looking at the first pointer in this object and seeing if it is this type that it expects. So at that point, okay, if this passes, if it gets through that, it knows the type of A. And then it does, like I'm reordering the things a bit, but it does 2 loads. So it loads the B property and it loads the bar property directly from memory. Then it calls this built-in. So here, like foo might be some function implemented in the engine itself, like a kind of standard library function or something like that. And then it directly stores the result back to C, right? So this would roughly be what a proper optimizing compiler does. If you try to verify that this code is correct and it doesn't do anything fishy, you'll probably have a bit of a hard time. So, I mean, here this is the kind of reasonable. Like to prove that these memory loads are correct, you have to go into this map object and also like parse the type object, this map object, and like verify that, you know, offset 8 is really property B or so, and offset 12 is property bar, and so on. And you kind of need to have some trust that this stays this way and it doesn't like later change, but otherwise, okay, you can kind of do this. Where it gets much more complicated is down here, where basically down here and down here, where basically, like for this store to be safe, there's a lot of assumptions that make this store correct. And so these assumptions are, for example, that the compiler can prove that, like there's maybe runtime information that tells the compiler, you know, property B of an A object is always this specific type, right? And so then it doesn't need to have a type check there. But also, you need to trust that the compiler's like side effect modeling is correct, because the compiler here definitely assumes that this built-in function doesn't have side effects. Like if the built-in function could run JavaScript code, we would be kind of back to the early example that I had where like you might change the type of these objects might change during foo. And then again, the store is not safe. So basically here you need to make a lot of assumptions or basically trust the compiler that it did the right thing, which is not what you want to do if you're trying to verify the result of the compiler. So yeah, this seems difficult, seems hard. Okay, so with that, that kind of brings us to the last thing. Can we somehow do something about this? And this is basically the idea that we had, and this is the idea behind the sandbox, is to basically decouple correctness from security, right? So we kind of concluded, okay, it is really hard to guarantee that we will always be correct, but maybe there's something we can do to not have every correctness issue be a security issue. Yeah, and so yeah, this is the sandboxing approach, right? So we accept that bugs will happen in this environment, but then we want to contain or limit what these bugs lead to. And specifically what we want to do is we want to have like, so what you see on the right here is kind of the user space of your process, and we divide that up into a sandbox, like a part of the address space that is the sandbox, and like the privileged rest. And then we want to make it so that all of these correctness bugs, they all just lead to corruption inside the sandbox, but they don't kind of corrupt memory elsewhere, like they don't spread to other parts of the process. I guess in an ideal world, like this would mean that in sandbox corruption is purely a correctness issue. Like this would be the ideal outcome. It seems a bit unlikely that we'll get there anytime soon, but this would be the motivation, right? Yeah, let's construct this. Let's see how this works under the hood. Basically, we take our user space, address space, and we take a huge chunk of it, maybe 1 terabyte. This is very cheap. On every modern operating system, virtual memory is very cheap. So we can just do that. Now this 1 terabyte is where all of V8's objects go. All of these JavaScript objects, the JavaScript arrays, these type information objects, everything that V8 operates on, it's all in this 1 terabyte region. Now, okay, what you're going to have is like references between these objects, right? So you have maybe one object has a property that points to another object. Pre-Sandbox, this would have been just a raw 64-bit pointer. But that is not compatible with the Sandbox model, because if you have a 64-bit pointer and there's memory corruption and this pointer gets corrupted, then it could point anywhere, right? It could point outside the Sandbox space. And if it then gets used in any way, like you would corrupt memory elsewhere, which is precisely what we want to avoid. So instead, the way it works is all of these pointers, they all become offsets, right? So in this case, for 1 terabyte, they would become 40-bit offsets, and then they would have to be added to the base address of the Sandbox to be used. Which then means, okay, if there's memory corruption and this 40-bit offset gets corrupted, doesn't really matter because it can only ever point inside the Sandbox still. Now then, the next kind of challenge here is that there's also external objects. You know, you have maybe a V8 object that references a DOM node, like a HTML element or something like that. So that HTML element, that's a normal C++ object on the C++ heap, not in the Sandbox. And so again, pre-Sandbox, this would have been a raw pointer. Again, this is not safe. And so instead, for those objects, we have an indirection. So in the Sandbox, you just keep a maybe 32-bit index that indexes into some table, and that table has the pointer and type information. And this is actually really, really similar to how like a Unix kernel, for example, works, where the index is basically a file descriptor, and it goes into a like table in privileged memory, and then that points to something. Right. So this is kind of the idea: get rid of all the raw pointers. In practice, it looks a little more complicated because everything is complicated in V8. But this is more closely to how it actually looks like today, where there's actually different types of tables, just because there's very different types of external objects. So for example, you have like machine code should also not be in the Sandbox. Like the raw JITted code lives in its own trusted space. And for that, there's a dedicated table that basically has the signature and the pointer, right? So you want to make sure that if you call a piece of machine code, that you call it with the right signature, because otherwise like stuff can go wrong. So there's a dedicated table for that. There's a similar thing for kind of trusted V8 objects. Like for example, there's JITted code also has metadata that is needed for de-optimizing code or like kind of managing code. And this metadata also must not be corrupted. So that must also live elsewhere. And so then there's a dedicated space and table for these trusted V8 objects and so on. But roughly speaking, the picture is kind of this of like offsets in the Sandbox, indices for everything else. So what I just showed, this is kind of how it looks today. In the future, one thing that I'm quite excited about is there's a potential for hardware support for this, which would, then it would really be very similar to how user space and kernel work, where if you run Sandbox code, you somehow drop the CPU's privileges, so it really cannot write to out of Sandbox memory, and it can only write inside the Sandbox address space. And yeah, this would be built on top of like the software Sandbox, which does all of this separation of objects, and it would add kind of a layer of security. I guess here the ideal final outcome would be that V8 would be comfortable running untrusted machine code in their Sandbox. Like you give it machine code and V8 is like, okay, fine. I like put the CPU in the Sandbox mode and then off I go, and this is fine. Again, this is not going to happen in the near future, but this would be the inspiration, let's say. I guess with that, so if you think about this, like I would call this maybe Sandbox version 2, like with hardware support. What it would mean is like you kind of split up your code into something you consider privileged code, which would be kind of kernel space, which can read and write everything. And then this must be careful or ideally like memory safe in some way. And then you have sandbox code, which can only write in the sandbox. And ideally, this is like where bugs no longer matter. And so if you think of V8, like V8 has a lot of different types of code in it. Kind of this is how it would probably be partitioned maybe, where the important bit is like this here, right? So all of the like JIT generated code, all of the interpreters, all of that stuff, this is where all of these bugs happen. All of this code runs sandboxed. And then on the other side, you have what cannot run sandbox is binding code, which is the kind of glue code to the rest of the process, to like the rendering engine and so on. Like this cannot be sandbox because it needs to integrate with out of sandbox objects. And then like you could maybe run actually the compiler itself in sandbox mode. It just seems like that would be a lot of work with very limited benefit, because the compiler is not actually corrupting memory. It's the code generated by the compiler that's corrupting memory. So that's what you want to run sandboxed. Maybe coming back to this picture I had at the start, maybe kind of the way to think about it is if you add sandboxing, you do again get some sort of like additional layer that's one step removed from the direct attack surface to protect your application. Cool. So I think that also already brings me kind of towards the end. So this is really the idea, right? So the sandbox, what it wants to do is decouple correctness and security in such that, you know, maybe generated code, it can still be incorrect, but at least it's secure, right? And then with the sandbox, these security properties are actually easier to verify. One example is since maybe, what is it, like November or so last year, there's now a bytecode verifier for V8. So this is the initial, like if you take JavaScript code, the first way it's going to execute is in an interpreter that runs custom bytecode. And this bytecode can now be verified to be safe to execute, right? And this is actually really simple in the sandbox model. So if you're interested, take a look at this document. But it really just boils down to like checking that the bytecode doesn't kind of do incorrect jumps and doesn't access registers like out of bounds. Like it's kind of really just two properties that you need to prove to be sure it's sandbox safe. Versus if you try to prove that the bytecode is correct, you would be looking at quite a big pile of work because there's all sorts of kind of subtle invariants that need to be correct for it to not corrupt any memory. Coming back to this code verification example, I want to show how this suddenly transforms to a much easier problem in the same way. So again, this was the example I had before of this function that like loads some properties, calls a built-in and stores a property, where we concluded it was kind of, it seemed hard to generically validate that this is always correct. So let's look at how this changes with sandboxing. The first thing that changes is that I said we can no longer have raw pointers, right? So these red instructions, they would no longer be, like we wouldn't compile our code in this way because we no longer have raw pointers. Instead, the code would look something like this on the right, where we are actually loading like 32-bit offsets from memory, and then we're adding them to the sandbox base. So maybe in this example, the sandbox base is always in register 13. I think that's actually exactly how it is. Like in V8, I think RS13 is always the base. So we are already paying like a little bit of a price here by having an additional instruction. But this would be the code that actually the compiler generates now with the sandbox. And so let's now this is actually quite a kind of a simple problem, because all we have to do to verify that it's sandbox secure is we have to validate that all the pointers point into the sandbox. But this is basically trivial because we always have 32-bit values that we load from memory. We add them to the base. And so there's no way this can be not in the 1 terabyte sandbox, with the assumption that R13 is correctly set. But okay, like that is one assumption we have to make. The second thing we have to prove is that all the offsets are inside, like are kind of less than the guard regions around the sandbox, so they cannot like reach out. In this case, this is also trivial because all the offsets are constants. It would get a bit more complicated with, like if you had dynamic indices, then you probably need some sort of additional clamping instruction, but that's also doable. And we do need to validate that kind of the jumps go to right places, but this is also doable. So I would say what we've achieved here is that with the sandboxing model, our code is actually much more amenable to verification for these security properties of the sandbox. Where it's at, so where we today, so the software-only sandbox is mostly finished and it's shipping in Chrome. Like the design level issues are mostly taken care of. There's like implementation issues remaining, by which I mean that basically what happened is, well, we added a new security boundary kind of in the middle of V8. And so now there was a lot of like code written pre-sandbox that was not safe anymore, right? Because it would make assumptions of the form that, you know, if I store something in the sandbox and then later read it back, it would be the same thing, but actually that's not true. So there was a lot of code that had to be like rewritten or at least refactored a bit. And there's still some remaining issues like that. The sandbox is part of the bug bounty program already, so if you find any issues, you can get money for it. And we do have a prototype for hardware sandboxing. It's based on like Intel's memory protection keys, which are not really made for this purpose. It's kind of misusing them, but it does work with some limitations, but it does work. Much more interesting is ARM's upcoming PoE2. So that's a similar like processor feature for kind of basically adjusting memory permissions at runtime in a more fine granular way. And this is really, like, this looks like it would be really powerful for this use case. What's left to do? There's actually kind of a lot of things that I think would be worth doing. I mean, the code verification is kind of one obvious example. We haven't actually built it, right? We have only so far been spending all the time building the infrastructure for the sandbox, but not actually building this verification on top of it. It would be worth, like there's still going to be a lot of C++ code that is privileged in some sense. So it would be worth investigating or investing in memory safety feature for this like privileged code. More hardware sandboxing work should be very useful. I mentioned there's these trusted spaces in V8 itself. So this like bytecode or code metadata, they live in trusted memory. So there's room for hardening this trusted memory space. And then also like sandbox fuzzing is, I think, also an interesting topic to work on. Right, and that brings me to the end. So quick recap, what I've tried to explain is how compilers exposed to untrusted code, how that very quickly means that any correctness bug is also a security bug. And guaranteeing or proving correctness of one of these kind of complex real-world compilers is hard. And so instead, the idea behind the sandbox is to decouple correctness and security. And this is the goal, and this is what it tries to achieve. And I think this is a plausible path to actually getting a secure and high-performance engine at some point in the future. Great. Thanks a lot, and I'm happy to take questions.
Yeah, we already have a couple of questions, and we have the another microphone that's going to run around. First question maybe here, or yeah.
It seems that the kind of memory protection that you're looking into is similar to what is provided by Sherry. What are your thoughts on that?
Yeah, I think it would work. Like you could take Cherry's hardware features and like build the sandboxing like this. I guess it, yeah, I don't know. Like we haven't looked into building this ourselves. Like we focused on, like we mostly focused on ARM because that's where the customer base is right now, right? Like it's mostly Android phones that that would benefit from this. But I think it would be definitely a good research project. And maybe there was actually someone looking into this, but I think, yeah, it would be worth looking, like how can you make Cherry and make it work with this model? Absolutely.
Now that the sandbox is rolled out, did you actually see the number of exploits go down? Or has there been any kind of evaluation? How much it is helping?
It's ongoing. So like the story is a little more complicated. So we already shipped the sandbox in 2021 or 2022, I think. But it was like a really early version. Like the sandbox, what we didn't want to do is basically spend 5 years of engineering to build the sandbox and then launch like a massive change all at once, because that's going to be horrible. So it's actually all been kind of built in production, like while it was already shipping. I would say the sandbox has been kind of in a beta, I would call it, since like last year. The way we track it is basically this here. Like this spreadsheet. Like you can look at this. Yeah, the link is up there, but I'll post the slides. Or if you just search for this, you should find it. But we do kind of keep track of what are V8 bugs that we know are exploitable. Like we have a program where if you can write an exploit for a V8 bug, even if it's not your bug, even if you didn't find this bug, if you write an exploit for it and can like compromise a like server that we host ourselves, then you can get money for that. And this provides us with like a nice data set of these are bugs that were actually exploitable. And this is one way we do try to kind of quantify the impact of the sandbox. I think if you look at this now, you will see some sort of drop from 2024 to 2025. The sandbox probably has some effect on that, but it's not like, I would say it's like the progress bar is kind of here. Like I think it's going to be more interesting to see what happens when it gets to actually this point here, where like we still know of a handful of issues ourselves that we haven't gotten around to fixing. So I think that will be like the point in time to really check, did it have an impact on this data?
Thanks.
One question.
You focused a lot on JavaScript. What are your thoughts on WebAssembly as another source of bugs in the browser?
Yeah, so I mean, what I would say is WebAssembly seems like a much better language for this sort of application, because as I said a few times, right, like JavaScript is just so terrible for optimizing because everything can change all the time. And WebAssembly is much more strict, right? Like you have actually type information in the code. Like the compiler has a much easier job optimizing things. So I think it's the right, the better language for this purpose. What we have, so WebAssembly is like WebAssembly launched like 2017 or so, right? But that was a very simple version of WebAssembly. Like this was basically like what would now be called linear memory WebAssembly, where you really just kind of have like arithmetic operations and you have load and store from like one big array of memory. And this was quite simple and we didn't see many bugs in it. What happened later is, I think, maybe 2023-ish, what was called WASM-GC launched, which is a very harmless name for a huge bag of complexity, because WASM-GC basically added like a highly complex object model to WebAssembly. The goal was that you wanted to be able to compile maybe Java or like other languages that have like a garbage collector maybe. And so to make that possible, you needed to make WebAssembly much more complex and give it like an object model, like hugely complex type system, garbage collection support, and so on. And then we definitely saw like a huge bump in vulnerabilities caused by the additional complexity. I would still say WebAssembly is the better language, but it's not like it has, on some sense, it has caught up a little bit to JavaScript in complexity.
Just as a very quick follow-up question, to what extent can WebAssembly live in this sandbox?
It fully lives in the sandbox. Maybe if I show this slide also again, like all of WebAssembly's objects are also like this, right? So they all live in the sandbox itself, and also the linear memory WebAssembly, like these huge like raw memory areas, they also are just buffers in the sandbox space. Where it does create some friction is that if I show this slide again, like WebAssembly adds a bunch of objects here, right? Because WebAssembly needs like kind of management objects that describe the state of the WebAssembly virtual machine, and like, you know, where does execution continue later on, or where's my stack, or this sort of stuff. So it does increase, I would say, the attack surface. But yeah.
Thanks for the great talk. I wanted to ask about this bytecode verification. You mentioned that you could do it, but you don't yet do it. Is performance an issue, or like when would you even do bytecode verification?
It's a good question. So like where do I have it? So it's a bit unclear. Like we are currently experimenting with how we like run it, or when we run it. Like if it turns out to be like to not have much of performance impact, we would just run it all the time. The alternative would be you could do like stochastic based verification, like you could say verify 20% of the bytecode or something, which would mean that if there's a bug that leads to invalid bytecode, then there's an upper bound on the reliability of an exploit, which is whatever, 80% or 90%, which would be sufficient to heavily discourage real attackers from using them. So this would be enough. But like it's like the way to measure this is a bit slow, because you need to like you do like A/B trials in production on like stable population, and then like first you need to write the code, then you need to wait until the code ships in like Chrome stable. Then you need to do these experiments, you need to ramp them up like over time, like from very small populations. So it all takes a bit of time, but it's ongoing. Or like it would also be something like if you have, like I mentioned, there are these kind of settings for like more secure browsers, right? Like maybe there's a setting to disable optimizing compilers. Like you could also imagine that enabling all sorts of verifiers would be an option that a user could toggle if they choose.
I also have a question. Yeah, thank you. I also have a question about the type of attacks that are still possible. So it sounds like, okay, now the memory within the sandbox can't be trusted, and this could lead to data-oriented attacks. And some security researchers say that these are equally, if not perhaps like worse than corruption. So I was wondering, like, what are your thoughts about that?
Yeah, I mean, so what I would say is one thing that makes the normal JavaScript bugs really attractive is that they are very powerful. Like if you take these compiler bugs that I showed at the start, like they give an attacker a lot of flexibility to control kind of exactly when and how and what memory gets corrupted, right? So this is really powerful, and this leads to really reliable exploits and attacks. And so with the sandbox, the hope or the goal would be that you take these really reliable, powerful bugs, and you contain those, and what you then end up with is kind of a lower quality for an attacker type of bug that is less reliable and harder to exploit, right? Because maybe you could imagine, like what you said, now you introduce like C++ kind of maybe data races, right? So this is one type of bug we have seen a lot, is like double fetch style bugs where C++ code reads a value from inside the sandbox once, then does something, reads it again, and implicitly assumes that it didn't change in between, right? And if it did, it like goes out of bounds or something. But these bugs are certainly of kind of lower quality for an attacker, because they don't give you the same level of flexibility. And they are also kind of mitigatable in more generic ways, right? So if you think of, like if you actually did write this code in a memory safe language, this bug would go away. If you use maybe like memory tagging, like hardware security features, they can actually mitigate these like lower quality, like classic bugs. So this is the broad idea, like that these bugs are of lower quality. It is definitely true that we have had a lot of also high quality sandbox bypasses, which is why I'm saying it's still not quite where I want it to be, right? Like there is still, like for example, a high quality bug in the sandbox attacker model would be that you maybe are able to jump to a piece of code that isn't like what you expect it to be, right? And you run custom machine code. But it just seems like that attack surface is significantly smaller than all of your compilers, right? So yeah.
Thank you. Any more questions? If not, let's thank Samuel again.